When we designed Vega-Lite, we built it not just as a language that can be authored by people, but actually as a language where we can automatically generate visualizations. And I think that's also what distinguishes it from other languages such as D3 or ggplot in R. Because we're in JSON, it is very easy to programmatically generate visualizations.
You're listening to Gradient Descent. Today, we have Lavanya with us, who's been watching all the interviews in the background, but we wanted to get her in there asking questions. And we're talking to Dominik, who's one of the authors of Vega-Lite. And we got excited to talk to him because we've been using Vega in our product and we recently released it, but it solves this huge problem for us where we want to let our users have complete control over the graphs in a language that makes sense. And then we discovered Vega, and it was a perfect solution to the problem that we had. And then we talked to Dominik, and he had so many interesting ideas about the way machine learning should be visualized. And we didn't even realize he came from a visualization background. So we have a ton of questions to ask him today.
Super excited. Can't wait.
I think the main thing, or, you've done a bunch of impressive stuff, but the thing that is most exciting for us is that you're one of the authors of Vega-Lite. And so I kind of thought maybe the best place to start for some people who don't know even what Vega is just sort of describe what Vega is and what the goals are, and then how Vega-Lite works within that context.
Yeah. So the way Vega came to be is that my advisor, Jeff Hare, so Jeff, together with his graduate students, Arvind and Ham, created a declarative way to describe interactions, building on ideas from functional reactive programming, which is a concept that's been around for quite a while. And so they adopted this concept for visualizations to describe not just the visual encodings, but also the interactions fully declaratively. And so that then became, I think that was Vega version 2 at that point. Vega at that point was still fairly low level in that you had to describe all the details of the visual encoding, as well as the axes and legends and potential other configuration. So around the same time, my colleague Ham, who also worked on the first version of Vega, on this reactive version of Vega, he was working on a visualization recommendation browser. At that point then was called Voyager. And I helped him with it, and we needed a visualization language to do recommendation in. And so Ham and Jeff talked about the need for a high-level visualization language that you can do a recommendation where you don't have to specify all the details, but really only what's essential, which is this mapping from data to visual properties. So I think they talked at the Viz conference in Paris, and on the flight back, Jeff hacked the first version of it, which then I think the code is still what we're building on today.
That's awesome. Sorry, before you go too far down this path, I'm going to ask all the dumb questions that I feel embarrassed to ask. I mean, I feel like I've heard declarative language for visualization many, many times, and I always kind of nod, but what does declarative really mean? What would be another way that would be a non-declarative way to describe a visualization?
Yeah. The biggest distinction between declarative and on the other side is imperative, is that in a declarative language, you describe what you want, not how you want an algorithm to execute steps to get to where you want to go. Good examples of that are HTML and CSS, where you describe what the layout of the page should be, but you don't tell the layout engine to move something by a couple of pixels and then move again by a couple of pixels. Another good example of a declarative language is SQL. Or SQL, which is the database query language people use to query databases for both analytics or for, let's say, a banking system, for instance. And in these declarative queries, you describe what you want the result to be. So you say, I want from this table the tuples or the rows that have these properties. And you don't describe how you're going to get that. And that's as opposed to an imperative algorithm where you would have to write the search. You would know how the data is stored, in what format, whether it's maybe even distributed on multiple machines or not. In a declarative language, you only describe what you want. And then that could run on a small database that's embedded, or it could run on a cluster of 1,000 machines. And you shouldn't have to worry. And so for visualization, that means you shouldn't have to worry about how the visualization is drawn, how you draw a pixel here, a rectangle here, or a line there.
Mhm.
No, you just want to say, I make a chart that encodes these variables.
So I guess how declarative is it? Is it like, and I have used Vega a fair amount, but I think people
Mhm.
that are listening or watching may not have, right? So like I suppose the most declarative thing might be like sort of give me an insight about these these variables, or like just compare these variables, right? But that might be unsatisfying, right? Like what level are we like describing the semantics of what we're doing versus saying like, hey, give me these 3 pixels here, or do you say like exactly the type of plot that you want, or is that inferred? Like how do you think about all of that?
Yeah, the way what we built on is this concept called the grammar of graphics. And that is a really cool concept that a lot of languages like even D3 have built on. And the core idea is that a visualization is not just a particular type. So it's not just a horizontal bar chart or a bubble chart or a radar plot. But instead, a visualization is described as a combination of basic building blocks. Kind of like in language, we have words that we combine using rules, which is a grammar. And so the words in the grammar of graphics are two things. One is marks, and the other one is visual encodings. So a mark is, for instance, a bar or a line or a point. An encoding is a mapping from data properties to visual properties of that mark. So for instance, a bar chart is a bar mark that maps some category to X and some continuous variable to Y.
Mm.
And that's how you describe a bar chart. And now I think what's cool about this is if you want to change from a horizontal to a vertical bar chart, or some call it like a column or a row chart, you don't have to change the type. You just swap the channels in the encoding.
I have a question. So we see so many really messed up charts that people make because people get too excited, especially when they work with a really powerful visualization tool. And I feel like you've spent so much of your life designing really good grammar for visualizations and designing a lot of really cool plots. So what's your recommendation for people for best practices for designing these visualizations?
I think it is actually making mistakes. It is trying it out and seeing how difficult is it or how easy is it to read data in a particular chart. But before you actually go out and publish that chart and show it to the world, maybe think about what can I remove from this chart? I think a visualization is really showing what you want to show when it's showing the essential of the data. Very important in any visualization design is following two basic principles. And these are often called effectiveness and expressiveness. This goes back to some work from Jock McKinley, who developed actually an automated system to follow these rules. So these two rules, they're kind of oddly named, but essentially what they boil down to is, first, expressiveness means that a visualization should show all the facts in the data, but not more than that. So what that means is that a visualization shouldn't imply something about the data that doesn't exist in the data. And then effectiveness means make a visualization that's as easily perceivable as possible. And what that one rule that you can apply there is to use the most effective channels first. And the most effective channels are X and Y, or they're like length and positions. They're the best. And then afterwards, it's like color and size and some other things. So that's why bar charts, scatter plots, line charts are so popular, or it's so effective because they are using those very effective channels first. But there's also, sometimes you have to go beyond effectiveness. Yeah.
I always wonder, I mean, like, is there any room for like fun or like novelty in a good visualization?
Yeah, that's a good question. I like to actually think back to a paper from Tukey and Wilk there. They wrote in like the 60s, this one of the famous papers about exploratory analysis and statistics. And they talked about the relationship of statistics to visualizations. And so the paper is full of amazing quotes, and it's kind of amazing to read this today because almost everything is still true today. But one of the things they say there is that it's not necessarily important to invent new visualizations, but think about how we can take the visualizations that we have, or the essential of the visualizations, and combine them in new ways to fit new opportunities. And so I think there's a lot of creativity in making visualizations, even the simple ones, bar charts, line charts, scatter plots, but combine them in meaningful ways, also pre-transforming the data in meaningful ways. And so there can be a lot of creativity in there.
Do you have a favorite visualization that you think is maybe underused or that you'd like to see more of?
I think slope charts are kind of amazing.
Ooh, what's a slope chart?
What's a slope chart? So naming charts, by the way, is an interesting concept. If you think about a grammar, then the concept of naming charts is kind of odd.
Yeah, totally.
I'm going to reveal a secret, but at some point I want to write like a system that automatically names a chart, or the other way around. Give it a name and it tells you what the specification is. Okay, but going back to slope charts. A slope chart is, imagine you have two categorical variables, let's say 2 years, and you have data for those years. And now what you could do is plot that as a scatter plot. So on X you have the years, and on Y you have some numerical measure. You should then draw different categories that exist in both years as colored points. It's hard to see actually trends between those things, between those different years. But if instead you just draw a line between them, trends or changes, like they just jump out to you. And that I think is great. So wherever you have categorical data and like this bipartite graph, and just drawing a line instead of drawing points is great.
It's called a slope chart?
That's one name.
Cool.
One in the Vega-Lite gallery.
Oh yeah, we'll have to link to that. So I guess where do you think about the line between like Vega-Lite and Vega? Is it always like super clear, like what belongs where? Because I would think a declarative, I mean, they're both in a sense, right? A declarative language for charts, right? One's sort of just higher level and one's like lower level. So where do you draw the line?
So maybe before we go there, one important thing to keep in mind is that Vega and Vega-Lite added something to the grammar of graphics. Vega-Lite in particular added, for instance, support for interactions. So something that my colleague Hammond, Arvind and I worked together on, where we added some other kind of words or language constructs that you can add to make charts interactive. And we also add composition. And so these are high-level concepts which then actually compile from Vega-Lite to the lower-level Vega into, in this case, layouts and signals, which are these functional reactive concepts that Vega has. And so I think that helps me also a little bit understand the difference of where does what go.
And what is, composition, before I drop that?
Composition is being able to layer charts or concatenate charts. And we also have a concept called repeat, which is a convenient concatenation. And then faceting. Faceting is another word for is trellis. It's a way to break down a chart by a categorical variable. So for instance, if you have data for different countries, you can then draw one histogram for each country or one scatter plot for each country. Faceted charts are also great. Often faceting is a very powerful way if you have an additional categorical variable to show you data.
So is this like where you make, like a whole like array or like a matrix of charts? That's what I'm picturing with a faceted chart.
Yeah. So if you
like
wrap
a grid,
it, I guess it
like a
becomes
grid
a
of charts.
Yeah.
Yeah. I see. Okay.
Yeah.
Cool.
Yeah. So that's faceting. Okay. So you asked about that's composition, and then we talked about Vega-Lite.
Yeah.
I think the biggest difference really between Vega and Vega-Lite is the abstraction level. Vega-Lite compiles to Vega. So anything that's possible in Vega-Lite is also possible in Vega because of that. But it requires about 1 or 2 orders of magnitude more code in most cases. So that's one big difference. And how do we achieve that? Well, one, we have higher level mark types in Vega-Lite. So for instance, Vega only has a rectangle. And it has some more, but Vega has rectangles. Vega-Lite actually has bars as a concept. And so if you have that, you can have some defaults associated with that high-level mark type, which you then don't have to manually specify in Vega. In Vega-Lite, you don't have to specify it because it gets instantiated in Vega automatically. And then the other is sensible defaults or smart defaults. Essentially, you don't have to specify an axis. We'll make one for you. If you use the X or Y encoding. If you use color, we'll make a legend for you. If you use size, we'll make a legend for you. If you use faceting, we'll make a header for you, which is kind of like an axis. In Vega, you have to specify all the details of those marks or of those elements, those chart elements. You can still override the defaults in Vega-Lite, but by default, we will do something. And that's really what Vega-Lite is. It's a high-level language and a compiler that compiles from higher-level specification to lower-level Vega specification. Right now, we don't have a way to easily extend the high-level concepts we have in in Vega-Lite. We do have a little bit of an extension mechanism where you can add macros. So for instance, box plots in Vega-Lite are just a macro, which actually compiles to a rectangle, the line, and the little ticks at the end. And there's a bunch of other things that are just macros. And so one could actually build a language on top of Vega-Lite. And people have done that. Altair, for instance, is a Python wrapper or Python syntax, Python API for generating JSON, Vega-Lite JSON specifications. And there's other ones in Elm and in R, and in, I think somebody made one in Rust, and there's one in JavaScript. Oh, in Julia. Yes, there's one in Julia as well. It's actually a really good one. Mm-hmm.
I guess the R comment made me wonder if you have any comments on ggplot. I feel like that's often like a beloved plotting library. Was that an inspiration for Vega at all, or did you have reactions to it?
So ggplot came out a long time before Vega and Vega-Lite, and it also built on the grammar of graphics. At the time, really was the prime example for an implementation of the grammar of graphics in any programming language, really. It uses slightly different terminology from Vega and Vega-Lite. ggplot has definitely been a great inspiration, and we, like, when I say we, so Ham, Arvind, Jeff, and I have talked to Hedley Wickham before. Yeah, big fans of it. We actually considered using it for Voyager, but because Voyager was easier built as a web application, interfacing from a web application to R would have been a lot more overhead than building our own visualization library.
Totally. Maybe switching gears a little bit. One thing I thought was interesting about your background and interest is it's also machine learning. And I thought that was like pretty interesting and cool. I wonder if like machine learning has like informed your thoughts about, well, first, if it's informed your thoughts about visualizations at all. And then I'd love to hear about if you have suggestions of kind of visualizations that you think are helpful in the, machine learning process.
Mm-hmm. Yeah, I think visualization and machine learning are really good fits for each other. And so I can think of two things that we can talk about, both where visualization is useful for machine learning and where machine learning is useful for visualization.
Totally, yeah.
Maybe let's start with why visualization for machine learning. I think one of the most, you can disagree with me there if you want to, one of the most important things in machine learning is data. It's not the most.
I think few people would disagree.
Okay, so because data is so, we can agree that data is essential to machine learning. If you have bad data, your model is not going to do anything good. You can still create a bad model with good data, but good data is essential for a good model. And so understanding that data that becomes part of your model or gets used to train the model is really essential. And I think visualization is a really powerful way there to understand what's in your data, what's happening there, especially in conjunction with more formal statistics. But formal statistics are only good when you know what you're really looking for. When you're still trying to look around, what's in this data, what might be problems with the data, that's when visualization really, really shines.
And you actually built a library to help with the exploration of data, right?
Yeah, so Voyager and then Voyager 2 and some other follow-up work from there is a visualization recommendation browser. So the idea there is that rather than having to manually create all the visualizations and go still through this process of deciding which encodings do I want to use and which mark type do I want to use, just let you browse recommendations and still be able to steer the recommendations. So the recommendations shouldn't go too far from where you are. They should still be close to what you've looked at before, but they should take away some of that tedium of having to manually specify all the charts. And recommendation is great for two things. One is, because it makes visualizations less tedious, and also it can encourage best practices. For instance, good statistical practice, or good practice, data analysis practice, is to look at the univariate summaries when you start looking at a data set. So what are the distributions of each of my fields, each of my dimensions? And doing that before looking into correlations between dimensions. And this is often difficult if you if you start looking at one field and you're like, there's something interesting here. Now I wonder how this correlates with this other data set. And then you're off on a tangent. I've done this. you're off on a tangent. And so by forcing you, or by offering you a gallery of all the dimensions and all the universe summaries at first, it makes it a lot easier to follow that best practice of looking at all the universe summaries first.
Can you do this at scale? Like, will it scale to millions of rows? And how do you even begin if your data set is that big to find patterns in it? And how does the software scale to?
Yeah, so the software is built as a research prototype that is built as a browser application where all the data has to fit into the browser. So it currently does not scale. But the interesting thing about it is that the number of rows shouldn't really matter too much as long as we can visualize it. We could probably have a whole episode about that.
Wait. The number of rows shouldn't matter in what sense? Like, it seems like it would make it more complicated to visualize. I mean, it doesn't make the visualization necessarily itself harder, but it seems like actually like scanning through all of them might start to get impractical.
Yeah, it's I guess there's two issues. One is a computational issue of just transforming that data and then rendering it. And then the other is, can I represent the data in a way that is not overwhelming to the viewer?
Mm-hmm.
But assuming we can do that for like a couple thousands of data points, or tens of thousands or hundreds of thousands of data points, if you have many dimensions, the recommendation aspect gets a lot more difficult. Because now you have to think about, okay, how do I represent all these dimensions, let users browse them? How do I show correlations between dimensions? There's a lot more. And if I show all correlations between 3 dimensions, it gets impractical very quickly.
Totally.
Yeah. So that's I guess visualization for machine learning. And then going the other way around, machine learning for visualization is something that I've become pretty interested in. When we designed Vega-Lite, we built it not just as a language that can be authored by people, but actually as a language where we can automatically generate visualizations. And I think that's also what distinguishes it from other languages such as D3 or ggplot in R. Because we're in JSON, it is very easy to programmatically generate visualizations. Then we built a recommendation system on top of it. So when we have a visualization language that is declarative and in a language that is easily generatable, we could think about ways to automatically generate visualizations from programs or from models. And so one of those models is a model called Draco. My colleagues and I have been working on together, where we encoded design best practices as a formal model. And then we can automatically apply those best practices to recommend visualizations. And so that can go beyond what I've talked about in Voyager, where we recommend this gallery of visualizations, because you can consider a lot more aspects of both the data or the visualization or the task that the user wants to do or the context that they're in or the device that they're looking at it on.
It's funny. I keep wanting to ask, actually, I don't know how to fit this into the flow, but I think one of the issues with visualizing data in machine learning, especially with a lot of the deep learning folks that we work with, is that the data often it's not like the sort of 3 independent variables and a dependent variable in a stats class. It's more like the data is like a image, or the data is like an audio file. And so I feel like just even visualizing the distributions gets unwieldy, and it's also like a little unclear like what you would do with that. So like, do you have thoughts about visualizing things where there's like a higher order structure, like an image or a video or audio file or something like that?
That gets tricky because a visualization is 2-dimensional, 2-point something dimensional. Maybe you can use color and size, and every encoding channel essentially can represent another dimension. But after 4 or 5 or so, it really becomes overwhelming. So if you have a data set with thousands of dimensions, I think the way to do it now is to use dimensionality reduction methods. So t-SNE, UMAP, PCA, to reduce the numbers of dimensions to the essential, in some way, dimensions.
Got it.
Or create some kind of domain-specific visualization. So in a way, an image is a domain-specific visualization that maps your long vectors of numbers to a matrix of color encoding.
So, what do you think about all my Twitter feed is talking about model explainability and how that's still a very unsolved problem? So, what do you think are techniques that everyone should know about, and how do you think the field is progressing? Do you think we can have interpretable models in 5 years, anytime soon, or are neural networks never going to be explainable?
I don't know. That's a good question. I think many people are trying to answer. There's been a trade-off where people often made simpler models because they are more explainable, and the more complex the model gets, the harder they get to explain. So sometimes there's methods similar to dimensionality reduction, I guess, to reduce your complex model to a simpler model, which you can then explain. But none of those methods are fully really satisfying. Some other techniques I've seen is use more inherently explainable models that are still complex. So for instance, a good example of that are GAMs, general additive models, which are linear models of functions applied to every dimension.
Well, why is that more explainable?
Why is it more explainable? Because you can apply some techniques where you can understand, for instance, the function that gets applied to every dimension individually. Or you can also then look at how do those dimensions or the functions applied to those dimensions, how do those get combined in just a linear function, which is a lot easier to understand than some nonlinear combination of many dimensions.
But wouldn't you want to have the different dimensions interact with each other, or allow for that? I guess maybe taking a step back, can you kind of make this a little more concrete for someone who hasn't seen this before? Like, what kind of functions would you be imagining, and how would they be applied?
For instance, if you want to predict a quantitative variable, like some number, let's say use the standard example, the housing price, the price of a house. You want to do that based on the dimensions, the available dimensions. Let's say the size of the square feet, the number of bathrooms, the number of bedrooms, or the number of floors. And so now what you can do is do a linear combination of the dimensions to get the price. So if you just take a linear combination, you could say multiply the square feet by, I don't know, 10, the number of floors by 20, the plot size by 5, and then get a number out that is the housing price. So that would be a simple linear model where you essentially apply a weight to every individual dimension. So now what these additive models do is that they apply a non-linear function to each dimension individually. So it can be like a log function or any other complex. It can be as complex as we want. But because it's a function, you can actually visualize it very easily just by looking at the value on the x-axis and the value after applying the function on the y-axis.
Mm-hmm.
And so if you then want to know what is the price of a particular house or the predicted price of a house, in each of these charts per dimension, you just look up for my value, what is the corresponding value that goes into the sum, and then you just sum them up.
I see. So you can see exactly how much each thing contributed to your final score or your final prediction.
Mm-hmm. Yeah. And a very good example of, if you want to actually play with that and try it out, is this system called Gamut, which is a research project at Microsoft Research, where they built a system for doing exactly this task of understanding a model that is a general, one of those GAM models, and both being able to, for instance, compare two predictions for two houses, understanding how much each dimension contributes to the predicted price, and also make it very easy to compare or to look at the general model, the whole model, in just one view. And yes, you don't have the ability to have multiple dimensions affect your output, but still, these models work fairly well and are a lot more interpretable than a model that computes many dimensions or incorporates many dimensions in every single point.
Do you have thoughts on visualizations to help with understanding what's going on in much more complicated models, like say, like a convolutional network or a fancier type of network?
Yeah, I think visualizations can actually help at different points. And I think visualizations are only as powerful as, or only as useful as as the task that you designed them for. So I think in general saying, oh, can you visualize this thing is impossible without a task. So can you visualize X for Y? So for instance, one could visualize a model for the purpose of understanding the architecture. And so when you, for instance, have a complex neural network with many layers and many different complex functions in every layer, you might want to visualize it to see what functions are being applied, what parameters are being used, and how big is each layer. And so there's a couple of visualizations. I think one of the most popular ones is probably the one in TensorBoard, which actually my colleague Ham started when he was interning at Google. So that's one.
Did you mean the parallel coordinates plot, maybe? Or which visualization in TensorBoard?
In TensorBoard, it's the visualization of the graph, the data flow graph. There's kind of two views in TensorBoard. There's the one where you look at your model outputs or your metrics, and there's the one where you look at the model architecture. And I'm talking about the model architecture one. So that can help you to, for instance, debug what's happening, but it doesn't help you at all to explain a particular prediction, for instance. So for that, you might use a different visualization that does like feature visualizations or lets you inspect different layers or see attribution in different layers.
Cool. We always end with two questions. I want to make sure we have time for it. And I think we maybe should modify them slightly to focus on visualizations. So, normally we ask like, what's, a subfield of machine learning that people should pay more attention to, which I'm curious your thoughts on, but maybe I would also ask a sort of subfield of kind of visualization that you think doesn't get as much attention as it deserves.
I think for machine learning, I'm very excited that there's a lot more attention on understanding what's happening in these models. I'm also a huge fan of more classical AI methods, which I guess is not machine learning anymore. But yeah, I'm very excited about constraint solvers and
whoa, man, we have not had that
AI
answer.
methods.
Constraints? I thought you were going to say like SVNs or something with constraint solvers.
No, classical like AI, not even learned. Right?
I thought they used ML to do constraint satisfaction these days.
I guess.
I don't know.
Yeah. Well, you can use
awesome.
ML now for learning indexes and databases. So,
cool.
And I think these classical AI methods are exciting because they allow you to describe a kind of a model, a concept, a theory in a very formal way, and then automatically apply it. Very declarative problem solving and describing of problems and solving them. And these solvers are amazingly fast today. Pretty excited about it. In visualization, because it's a science, we're trying to explain what makes a visualization good. And there's been a lot of work on high-level design of good visualizations. So I talked about these principles of effectiveness and expressiveness earlier. And there's now systems to automatically apply them. And there's design best practices, and there's books, and people are teaching those in classes and so on. And then on a very low level, perceptual level, there's some understanding of how do we perceive colors and shapes and gestalt of shapes. And how do we see patterns? But we don't have a good understanding of how those low-level insights on perception actually translate to those higher-level design practices. And I think the two sides slowly are inching towards each other, but they're not they're like this far from each other right now, and kind of slowly inching towards each other. And what I'm excited for is it's kind of like the general relativity theory of how do these two actually combine? We need a unifying theory there of how do these two things relate. It's like we know it's high level. It's kind of like relativity. And we know these small like quarks things, but we don't know how they relate to each other. We know how the universe behaves. We know how little particles behave. But when you combine it, it doesn't work. And so we have kind of this crisis that physics has had for a while as well in visualization.
Well, what a great answer. That's so evocative. I want to talk about that for another hour. Normally, we end with asking people really on behalf of our audience, kind of what the biggest challenges are that you see in taking ML projects from sort of conception to deployed. Do you have thoughts there?
I think one of the trickiest thing in deploying machine learning are metrics. Coming up with good, meaningful metrics that you're optimizing. To me, machine learning it's optimizing a function. But what is that function? And how do I make sure that that's actually a meaningful function? And also that it's going to be meaningful in the future. Because we know from many examples that if you're over-optimizing a metric, that metric becomes meaningless. So how do you ensure that a metric is meaningful right now and will be meaningful in the future and is actually tracking what you care about? It's a difficult question, and I don't know whether there's going to be one answer. I don't think so.
Train a model on a bunch of different optimization functions and figure out which one made sense or something.
Yeah.
But I kind of want to specifically ask about what are the biggest challenges around machine learning interpretation, and also when you're training models using visualizations to debug these models. Do you have any thoughts around that, maybe?
As I said earlier, I think data is essential for machine learning. And so understanding data is crucial. And I don't know whether the methods and tools we have for general data analysis, how much they might have to be adjusted for machine learning. Does, for instance, Tableau or Voyager, all these tools that are designed for exploratory analysis of tabular data, where do they fall short when it comes to machine learning? Lucas was pointing out earlier that machine learning often has this high dimensional data, images and sound and so on. Can we design other representations? I don't even want to say visualizations, but just representations that help us see patterns in that data, meaningful patterns, meaningful for the task of training a model or understanding a model. That, I think, is going to be an interesting question for visualization tool designers who like to work in the machine learning space going forward in the future.
You know, it's funny, like, I feel like one thing that everybody working in machine learning misallocates their time a little bit, including me, is I feel like you almost always spend too much time looking at aggregate statistics versus individual examples. Like every time you look at an individual example, you're just like, oh, like I can't believe I missed this stupid thing that, you know, is breaking my model or like making it worse in some way. And so I wonder if the gap is like, we have really good tools, I feel like, for aggregate statistics, but it's hard to like quickly drill into stuff, especially when your data sets get very large.
I believe actually that I totally agree that we have very good tools for looking at aggregate statistics. I think we also have reasonable tools for looking at individual examples. Like we can look at an image, that's okay, or at a row in a table. But I think where it gets really tricky is understanding the in-between. So understanding the subgroups that exist in the data. And that is because there exist n choose m possible subgroups in a data set. And if you have a million rows, that's a lot of subgroups. And only very few of them are actually meaningful. So understanding which subgroups are behaving oddly or are negatively affecting your model and looking at those, that is a challenge that I see over and over again. I think this problem of not aggregate and not individual, but somewhere in between. And where in between do I want to look? That to me is where the difficulty lies.
All right. I think that's a nice note to end on. Thank you so much.
Okay.
That was really fun.
Yes. Thanks for all the questions and everything.
Thanks for listening to another episode of Gradient Descent. Doing these interviews are a lot of fun, and it's especially fun for me when I can actually hear from the people that are listening to these episodes. So if you wouldn't mind leaving a comment and telling me what you think or starting a conversation, that would make me inspired to do more of these episodes. And also, if you wouldn't mind liking and subscribing, I'd appreciate that a lot.